Let's now start with the topic of work and energy, starting with the concept of work and power. We're all familiar with the concept, or at least the basic concept of work. Whenever we do something, when we walk, run, push something, lift an object, carry an object from one location to another, when we open the door, and so on, we are basically performing work. And put in simple terms, energy is the capacity to perform work. When you have energy, you can perform work, and when you perform work, you use up energy. Energy is the capacity to perform work. We use variable E, at least for this equation. We use E for energy and capital W for work. Energy is the capacity to perform work. When you have energy, you can perform work. When you perform work, you use up energy. As such, energy and work both have the same unit, Newton meter. Newton meter has an equivalent unit, joule, or capital J. So 1 joule is the unit for energy and work. And we perform work when a force is applied on an object and the object undergoes displacement. You have an object and you have a force applied on that object. If that object undergoes a displacement x, that force performs work W. And work W in this instance is equal to integral of force dotted with dx. So note, this is that product. And by definition, that product is vector dotted with another vector. And that is equal to magnitude of the two vectors multiplied by cosine of the angle between the two vectors. So f dotted with dx is magnitude of f times magnitude of dx cosine of angle theta, the angle between f and dx. So work done is equal to integral of f dx cosine theta. Force, Newton. Dx, very small displacement. So that's basically meter. So 1 Newton meter equivalent to 1 joule as we have mentioned earlier. Now note that product is multiplication of two vectors. And the answer is a scalar quantity, which means work, and hence energy is a scalar quantity. Now, cosine theta, from trigonometry, we know that cosine theta may be positive or negative. That means, depending on the angle theta, the work done by a force may be positive or it may be negative. Now, what does it mean for work to be positive and for work to be negative? When work done by a force is positive, the force that produced that work, that performed that work, that force F tends to increase the motion of the object. For example, the effect of the force on the motion of the object is to speed up the object. When the work done by the force is negative, that force F tends to lessen the motion of the object. For instance, The effect of that force is to slow down or decelerate the object. So again, work may be positive or it may be negative. So don't be surprised if later on in your calculation you get negative work. That's because of angle theta. If we get the rate at which work is performed or delivered, we have power. Power is the rate at which work is performed. Power, capital P, is equal to dW over dt, rate of change or rate of delivery of work with respect to time. Differentiation of work with respect to time. If we get the average power, this equation, dW over dt, reduces to work total divided by total time T. So P average is equal to total work done divided by total time. Power basically is equal to work divided by time. Work is joules, time is seconds, so unit for power is joules per second. This is given its own unit, watt, capital W. We have another unit for power, horsepower, typically used with machines. 1 horsepower, HP, is equivalent to 746 watts. Since work is a scalar quantity, time is also a scalar quantity. Scalar divided by scalar will give you a scalar quantity. So power is also a scalar quantity. Now, force may be constant or it may be non-constant. For constant force, our equation for work done, integral of F dotted with dx, if the force is constant, force is taken out of the integration. We are only integrating dx. Integral of dx will give you x. So for constant force, the work done by the force is just equal to F dotted with x. F dotted with x, dot product, by definition, that's equal to magnitude of F times magnitude of x times cosine of the angle between F and x. So work done by a constant force is equal to Fx cosine theta. And if we get the average power for work done by a constant force, average power is equal to work total divided by total time. That's basically F dotted with x divided by time. We have x divided by time. That will give you F dotted with average velocity. So, average power is also equal to F dotted with average velocity in addition to work total divided by total time. So, that product, by definition, F dotted with B average is equal to magnitude of F times magnitude of average velocity times cosine of the angle between F and V average. Now, what if the force is not constant? If the force is not constant, you go back to our basic definition of the work done. Work done is equal to integral of f dotted with dx or integral of f dx cosine theta. And you substitute the equation for f into the equation. For instance, if f is equal to, say, kx, some constant k multiplied by x, so f is equal to kx, you replace f with kx, so you have integral of kx dx cosine theta. And then you perform the integration. But if the force is constant, you use work done is equal to f dotted with x is equal to fx cosine theta. And that's it for now. In the next video, we'll continue our discussion on work and energy by looking at one type of energy, mechanical energy. So again, that's it for now. Thank you for watching.